Okay, section 4.8, sorry, part 2, 4.8, part 2. We're on the second page of your notes. Today, this part, we're going to be talking about turning points. Another important characteristic of a polynomial function are their turning points, which correspond to local maximums or local minimums. So I'm just going to go ahead and I'm just going to draw a random function here that kind of does a little swoop-de-swoop. Okay, go ahead and just graph that random function there. Okay, the turning points are where the function turns from going up to going down or going down to going up. It's basically where the function turns. Okay, and these turning points correspond to local maximum and minimums. Okay, and we're going to talk about the difference. There's two different types of maximum and minimums. There's local and there's what we call absolute. Okay, so we're going to talk about the difference. Some locals are also absolute, but some are not. Okay, so if we look at our turning points here, this one, again, we always read a graph from left to right. So as we read this graph, it's going up, and we get to a tippy topmost point here, and then it starts going down. So this is a turning point, and this turning point is a local maximum, okay? Because it's the highest point based on the points around it, okay? And then it starts going down, and then it reaches this bottommost point before it turns around. So again, there's another turning point, and this turning point corresponds with a local minimum. Okay, but these local extrema, that's what we use for max and min, but these turning points, this local max and this local min are not absolutes. The local max and min are just the highest or lowest points based on the points around it. Okay, so if we're just looking at just this one little piece of this graph, okay, we can see that we're going to have a maximum there. But if we look at this graph as a whole, this isn't the highest this graph ever goes, because it comes back down and then it goes up for forever and forever and forever. So this graph's going to keep going up forever and forever and forever. For this one, it has no absolute maximum. This one doesn't, because it's going to go up for forever and forever. Same with the minimum here, where this is a local minimum, but it doesn't have an absolute max or min. The absolute max and minimum, max or, I guess we should say max or minimum, is the very most highest point the graph ever goes. Okay, it's the highest or lowest point the entire graph ever reaches. Okay, so in this case, this graph has no absolute maximum and it has no absolute minimum, because this is going to keep going down for forever. Okay, an example, let's do a little sketch. I'm going to sketch a little one over here that actually does have an absolute maximum. Okay, so let's look at one. Let's say it comes up, does a little bump, comes up, does another bump, and then starts going back down. Okay, so it has a local maximum here. It has a local minimum here at this lowest point, and then it has a local maximum here. So both of these right here are what we call local maxes. And this guy here is a local min. Okay, but this point up here is also the absolute maximum, because this is as high as this graph ever goes. The graph will never get any higher than right here. That's as high as it ever goes. But this has no absolute minimum, because it's going to keep going down for forever. Okay, kind of see the difference there. Okay, all right, there's a couple little rules to help us know how many turning points or how many maxes and mins it's going to have. The graph of every polynomial function of degree n has at most n minus 1 turning points. Basically what that means, if I have a function that's x to the 5th, it can't have it will have no more than 4 turning points, one less than its degree. It might have less than that. It could have no turning points. It could have 1 turning point. Okay, it could have, it could have 2 turning points or 3 turning points, but it'll have no more than 4, okay, because it's x to the 5th. Okay, if it's an x to the 6th, it would have no more than 5 turning points. Okay, now if that polynomial function has actually n distinct, that means n different real zeros, then it will have exactly n minus 1 turning points. So if I have a function, and let's say this function is x to the 4th, blah, 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 I don't know the rest of it, but I know it has 4 different real, not imaginary, zeros. Let's say it has the zeros 0, 1, 5, and 9. So it has 4 distinct, and they're all different. None of them has a multiplicity of 2 or 3. 4 different real zeros. Then I know this will have, then I know this has exactly 3 turning points. Okay. Again, these are little tips and tricks, but with the invention, these used to be way more important back before graphing calculators, but now we can kind of just graph them, look at the graph, and determine how many turning points. Okay. All right, but they're little tips and tricks, little rules. If you want to remember them, go ahead. All right, so here for example 3, we want to graph each function. We want to identify the x-intercepts and the points where the local maximum and local minimums occur, and determine the intervals for which each function is increasing or decreasing. So this has a bunch of different parts, so let's do each part. First, let's graph each function. So let's graph this first function. I'm going to graph it using my calculator. Okay, so we have x to the 3rd minus 3x squared plus 6. Okay, x to the 3rd minus 3x squared plus 6. So let's look at the graph of that. Okay. So let's go ahead and let's trace. Let's find some points. 0, it goes to the point 6. 0, 1, 2, 3, 4, 5. Let's go up one more, 6. At 1, it goes to point 4. 2, is it 2? 3, is it 6? Okay, let's do -1. We're at 2. -2, -14, let's go -1.5. 1.5, we're at down, -1, 2, 3, 4, and a little more. Okay, so it's kind of going to look like that. So, come up, and down, and up. Okay. So there we have our graph. Okay, identify the x-intercepts. So we're going to identify the x-intercepts. So identify the x-intercepts. It looks like this one has only one. This one right here. Point right there. Okay. We're going to go ahead and I think we're going to find that using our calculator. Okay, so we'll go ahead and actually, if you didn't know this, I'm going to show you all kinds of tools with your calculator today. We can use our calc button. Do you see there? It's right above trace. Second, trace. And we want to find this intercept, which is also called a 0. So we're going to do option 2. Oh, there went my pencil. I've got to back up. We're good. Okay. All right. And it asks now for left bound. Basically, I need to be on the left of that 0. Well, that 0 occurs here, so I'm going to be on the left. There, my cursor's flashing right there. Yep, that's on the left. Enter. Now it asks you to be on the right bound. So now I'm going to be on the right. And do you notice here I'll put this little arrow? It's telling the calculator where to look. Look in this little interval. So look in between this 2 interval. Hit enter. So my intercept looks at approximately -1.1956. So that'd be 1.2. So my x-intercept, write that down, is approximately at x, approximately, this is us rounding, -1.2. There's us rounding. Okay. So now it asks us to, the x-intercepts, the points where the local maximums and local minimums occur. So we want our local maximums and local minimums now. Well, it looks like we'll have a local maximum up here, local minimum down here. Okay, so we could start doing some zooming in and approximating. I'm going to let you approximate with your calculator. Again, the second calc option. If you notice, we have options 3 and 4 for max and min. So this one up here is the maximum. So that's option 4. So I'm just going to type in 4. Again, it goes left bound. So I want to be on the left side of that maximum. That looks good. Hit enter. On the right side, hit enter. And then it asks for a guess. I never guess. I just hit enter. And so that maximum occurs right there at 1.96. Okay. But you can always, I don't know, we're good. We'll just leave it. 1.9. That doesn't seem like 1.9. I'm thinking there's an error in my calculator, but let's double check. Oh, because it was 10. Ooh, we got to be careful. This is 1.9. See that e to the negative 6? That means times 10 to the negative 6. So it's negative 1.9 times 10 to the negative 6. Do you see how very, very small that is? Okay, so that actually corresponds with 0. Do you see at 0 we get 6? So the calculator is just rounding. It's giving you an approximately. Okay, so, but 1.9, if we go back to 1.9 times 10 to the negative 6, look at how small, it doesn't even try it. It's moving the decimal back 6 places, so it's that small. So that actual maximum occurs at the point 0.06. So you can't just take what the calculator says and be like, yep, that's good. You have to look at that, read the whole number, make sure it doesn't have an E on the end. If it has an E on the end, then that's a super, super small number because it's times 10, or a super, super big number, depending. But it was to the negative 6, so that's small. Negative 6 right there. Remember, that's a really small number from science. Okay, so that's the calculator's approximation. We know it's exactly at the 0.06. Okay, so let's go ahead and let's find the minimum. Option 3, so left bound to the minimum's occurring right about there somewhere. Right bound. Okay, it gives me 2.00000023. Okay, well that's pretty much the 0.2. And if we trace and type in the 0.2, we get a minimum of 2. So that minimum then occurs at the 0.22. That's where the minimum occurs. So now, this last bit, we want increasing. Determine the intervals for which the function is increasing or decreasing. Okay? So, we want to look, where are we going up, where are we going down? So, as we read this from left to right, right here we're going up, so this is increasing. We increase until we get to this maximum, and then we're going to be decreasing, and then we're going to be increasing again. Okay, so I'm going to come in and I'm going to draw, so we're increasing from forever this way all the way to this right here. So we come in and I'm going to do highlighted. So we're going to be increasing x to the left of 0 here. So we could go ahead and write it that way in words. We're increasing to the left of 0. Okay. A shortcut way of saying that is x's that are less than 0. Okay, that's the shortcut way of saying it. Okay, this mathematical way there, and we're decreasing there in between these two greens. So in between an x of 0, again we describe increasing and decreasing in terms of their x. In between 0 and 2, so we're going to be decreasing for x's between 0 and 2. We can write it that way in words, or we could write 0 less than x less than 2. Okay, there it is in symbols. But then now we're increasing again to the right of 2. Okay, so we're increasing left of 0 and to the right of 2, or for x less than 0, x greater than 2. So we're actually increasing on 2 different intervals. We're increasing down here, increasing up here, decreasing in the middle. Okay, all right, we're not going to do this next one. Okay, so we have one more thing to talk about and then we're done.